All right, so today we're talking about hypothesis testing. Confidence intervals gives you estimate because a statistician would always take into account variation. Tests of hypothesis are trying to take into chance variation to see whether our result is plausible or too implausible to accept. So we have going to do hypothesis testing from section 8.1. You really should read section 8.1 all the way through 8.5. It's all kind of interrelated. There's usually a big 5 introductory statistics course. We'll look at 2 of those big 5. One is if you have categorical data proportions. That's a z-test for one proportion, or a sample mean, and generally that's associated with a t-test. So in general, statistics is really more like science because science uses a lot of statistics to make conclusions. You sort of ask a research question, you design a study and collect the data. That's really where statisticians make their money, is designing the study and collecting data. You explore the data, and then you draw inferences. You either take an estimation, that's confidence interval, or you do the logic of inference, which we're talking about today. And then you sort of formulate conclusions. Then you look back and ahead, say, well, what if we did this, or what would happen? What's getting us closer to the part? So there is this process of statistical investigation that we should kind of take into account. So at the end of Friday, we're talking about farmed salmon. There's some dispute about this, is whether this causes more harm to the environment. Farmed salmon is not as healthy for you. There's not as much omega, whatever those things are, omega-3 acids or something. There's all sorts of ideas around this. So we took a look at this example. They had 150 farmers. It's mostly random. You could find the standard. You found the mean of 0.09134. Your standard deviation was 0.4952. And the standard error of the mean was 0.404. So the upper bound for this turned out to be 0.098. These are not proportions. These are the parts per million of this Minex in these salmon that they sampled. So again, what you would have gotten was x bar plus or minus z star times the standard error. And so in this case, that's going to be a challenge. 0.0913 plus or minus our standard error, which was 0.00454. And then I think, is it 1.645? It is for the normal distribution for 95% confidence interval? Or is it 1.96? Oh. Is it 1.96 for set 97?
Yeah.
And so if you took this, 1.96 times this, the 1.0045, we actually want an upper bound here.
Oh, yeah.
So in that case, I'm doubting myself. So the inverse point norm of 0.9501 is how much? Can somebody just double check that out? This would be if we actually calculate it and didn't just have Minitab do all the work for us.
1.645.
Okay. 1.645. And I'm hoping that if you multiply these two numbers and add it to 0.0913, you would get this upper bound of 0.098. So I'll first answer Abby's question, and then we'll go to...
Are you doing inverse normal to 0.95 because you don't have to do the bottom?
Right, because we're only doing one-sided. Yes, that's right.
Yeah.
That was the question, yeah. And so you can either trust me or someone, you can have someone in the class see if the interval is that mu is less than 0.09803. You just trust me, or you're going to have someone check on me.
I got, did you get 0.09799?
Yeah.
It should be 404, not 45.
Oh, I'm sorry. How about there? See, you can't trust me always.
You got a number very close.
I got .0979.
You got 0.9 what?
.0979. That's pretty close.
Yeah. Well, it could also be that they used maybe I used a t-distribution instead of a z-score.
Maybe if they use the complete value of 1.645, because it's...
Yeah.
I did that.
What is the inverse t of 0.95149 equal to?
With the degree of 149.
Yeah, degrees of freedom is 149.
1.66.
66 what?
It's 1.655.
1.655?
Yeah.
And if you use that one instead of 1.645, what did you get? What do you get then?
You get the number you got.
Yeah, I forgot. I thought I ran a t-test on this one. See, so 6 days ago when I ran the test, then that's what I got. So, Tegan.
On a test, let's say n is 150, do you want us to still do t-test, or will you specify? Or will it have a question like compare the two answers?
Yeah, it's one of those judgment calls. When you get that high, once you get above 30, 40, or 50, first of all, the t and the z are pretty much the same, and also the population standard deviation, the sample standard deviation is the same. I'm sort of the opinion that you always use a t-test because you don't know the standard deviation, because now you can do it on the computer in the calculator. The thing about your table, your book has tables, and they didn't want to publish all of these things, so they stopped at 30. But now we can calculate it, so we might as well use a t-distribution. It's going to be a little wider. If you're close enough, I usually accept that. So we're 95% confident that the true mean of Myrex and farm sim is at most 0.903 parts per million. Again, make sure you have, like in your homework tomorrow, you post your confidence interval statements so I can kind of give some feedback on that. Abby? We'll go right to left here.
When exactly are we using the t-distribution only when we don't know standard deviation?
When you don't know the standard deviation, you're supposed to generally use the
So if
t-distribution.
you do know it, you still use the t-distribution?
What is that?
When you do know the standard deviation?
Oh, when you do know the standard deviation, then you use it. That's very, very rare in practice. And again, once you get above 30, the t and z are, it's not really that far off. 1/100th of a point.
So if you know the standard deviation,
You should use the z-test.
not t.
Yeah, I don't know where you would know the standard deviation in
What
practice
if
before.
your n is less than 30?
Then you definitely have to use a t-test. Yeah. Okay, next question. Yeah. okay.
Yeah, I mean, that was kind of my question, but you said, like, since we're able to calculate the t-distribution, when would we use the z-distribution?
If you knew the standard deviation and you knew that the distribution was normal.
But in that case, are we also still able to use the t-distribution?
You really should use the t-distribution if it's less than 30, even if it's coming from a normal distribution, because there's some problems with the tails.
So how come when you have like an upper or lower bound, then you can just use like the 0.95? Why would you not just use like the 0.05?
Remember, this is the inverse norm. There are two questions I think you had. One was whether or not you have a two-sided test or a one-sided test. If you put 0.05, you would just get negative 1.645, so it's, you're really not, it's almost the same thing. Okay.
And then it's just giving you what's below.
Yeah. You can either calculate this one, the 1.7 something, or negative 1.7 something.
Okay.
It's generally, though, that the notation is t of 0.05 is kind of the general notation that we use. Okay, but there's another question that we might have. What if we wanted to check the farmer's claim that Myrex was less than 0.10 parts per million? He doesn't he wants to show that yes, he's meeting EPA guidelines or something like this. Okay, so this kind of leads us to hypothesis testing. Is the claim too implausible to rule out by chance? So I go in there and I say no. I say it is 1.1 parts per million. So here's kind of the general process that we'll go about. First of all, we're going to state the test. This is a one sample t-test for a single mean. Okay, and then I'm going to say, I'm going to take some hypothesis. My null hypothesis will be that the mean is greater than or equal to 0.10. In this case, I'm just going to say 0.1. You could say u is bigger than 0.10 versus the alternative that mu is actually less than 0.10. So from your reading in Open Intro, where you were talking about hypothesis tests, you assume, sort of like you're assumed innocent until proven guilty. In this case, I'm trying to say that the farmer's claim is not true. So the farmer's claim is showing me that my claim is not true by saying that the mean of that chemical is greater than or equal to 0.0 versus the alternative that's less than 0.0. So then we look at the assumptions. So we have to look at randomness, normality, and maybe the level that we're going to check. In this case, we're going to check at 0.05. And then we're going to look at the results. And here's the descriptive statistics that I got from the null hypothesis that mu is 0.1 and the alternative is 0.01. I got a t-value of negative 2.14. So if I would have calculated everything and taken 0.09134 minus 0.10 and divided by s over the square root of n minus 1, or 0.04952 divided by the square root of 149, I would get a t-value of negative 2.17 from 2414.
Why do you use 149 as opposed to 150?
The degrees of freedom for a t-test, you take one less than your sample size. Because we know the mean, that gives us one condition that we have. So we can take that. I would draw the picture. Always draw the picture. There, I drew the picture. See, I drew the picture. And at negative 2.14, the area... Oh, I drew the wrong picture. No, I did draw the right picture. The area down below here is 0.017. And that's what's called the p-value. We'll talk about the p-value a little bit later. And since the p-value is equal to 0.017, which is less than 0.05, I'm going to say we reject the null hypothesis. So we have evidence, and then write my conclusion. We have evidence, not strong evidence, but some evidence. The MIREX, the MINEX, the MINEX, MIREX levels are less than 0.10 parts per million. So that's just the general sort of setup, and we'll kind of unpack each one of those. Lauren?
The T formula, it is n minus, like square root of n minus 1 instead of just square root of n. To find the T value. X bar minus mu over sample standard deviation.
Oh, yes. That was your question, right?
Kind of,
Yeah, so I did make a mistake there. That this is 150. Because it is S over the square root of n. You're right. I was thinking about the degrees of freedom. So it is S over the square root of n. Yes, Gabe? But the degrees of freedom is n minus 1, yeah.
Is the p-value just area to the left?
Yes. But let's kind of unpack this because you've seen it before, and let's go through the process of how you get that p-value. Jonathan?
What does the S stand for in the sharp axis?
Yeah. If you look at your book on page 83, actually, the wrong odd number. Huh. Where did I put my... Was I in the wrong class? Was I in advanced stats instead of math stats? And maybe I deleted it. Oh, we don't have to use this. Man. I don't know if it exists. Jonathan, not in your book. This is the kind of the setup that Dr. Eggleton uses, and I was going to try to play off it by playing that annoying little ditty. But I don't think I put it in there. It was just supposed to be a way to kind of formalize it. This was supposed to be state the test. And then give the hypothesis. Check the assumptions. Examine the results. And then make a conclusion. But there are many ways that people set this up. There's like the phantomist approach. It's generally this procedure. And we will, we'll be kind of strict here at the beginning and then move on a little bit. Okay, let's kind of go back to where we were at lab 3.
So, I have a question about this example.
Yep.
And the p-value and whatnot. So, the PDF that we see here is for the null hypothesis.
Yes.
Which in our case, so it's the probability distribution function for the mean
of 0.10.
Of 0.10.
Yep.
So if we find from
assuming let's write it this way. Assuming mean was 0.10.
Yeah.
The likelihood we would see something at negative 2.14 or more extreme would only be 1.7% chance.
Okay.
And we would say that's really too implausible for the way we've set this up. The mean can't be 1.0, and so we would say, or greater than or equal to 1.0. So we take the alternative that mu is less than 0.10. Okay, so back when we had lab 3, are females discriminated against in promotion decisions made by male managers? And you looked at this chart here. Well, not yet to the chart. But remember, there are 48 male participants. They were given random personnel files. They were identical except for the names. Half were male and half were female. Should the person be promoted to a branch manager position? So we talked about, is this an experiment or is this an observation? This is kind of an experiment because we're influencing them with parts. And so what you did was, here was the result, that 21 out of 24 males were promoted, while 14 out of the 24 females were promoted. But remember, we could say, well, that could just happen by chance. It was just a situation of randomness that happened. And then what you did is you ran some experiments with some cards. The idea was, the null hypothesis were that the variables were independent, being gender did not have any impact on whether they were promoted or not, even though all their files were identical. Or the variables are not independent, and the promotion rate of 29.2% was not due to chance, and equally qualified females were less likely to be promoted than males. And you got out the deck of cards. I keep anticipating the next part, it's not there. Okay, so you have a hypothesis test. It's a statistical test used to evaluate competing claims against using data. Usually the null hypothesis is sort of like it takes a no stance of no difference or no effect. And the alternative is there is a difference, there is an effect on this part. So when you wrote this down back in Lab 3, the variables of gender and decision are independent versus the alternative that they're not independent. And so what you did is you shuffled cards. 24 were, the black cards were male and 24 the red female. And you shuffled up and counted the number of times that would happen, the percentages, and you calculated the percentages that way. And so in this case, the only time that you would get something as extreme as this was 2 out of 100. Still could happen, but it was so implausible that we really had to rule out chance as the reason for the difference. There was something else going on, the alternative was going on. So in some sense, this is a p-value right here. The probability that you would see something as extreme as this, given the null hypothesis that there was no difference, would only happen out of 2 out of 100 times. That was really too small, 2% chance of seeing this by chance, too implausible. So you reject the null hypothesis and take the alternative hypothesis. I don't know, was that too long ago? Do you remember doing such things as this? I guess that's a question. That first one is no, and the next one should be yes. So I don't know if you question you answered. So that's the idea. Can you rule out chance as the reason for the observed difference or not? So we reject the null hypothesis. We concluded the difference in proportion rates of 29.2% was not due to chance, and equally qualified females are less likely to be promoted than males. So the point is to rule out chance as the reason for the differences. So, is it too unlikely to be believable? Okay. Is the study results unlikely to have arisen by chance alone? Is the difference between the model hypothesized and the observed data statistically significant? Is that difference just too unlikely by chance? Remember my Uncle Elmer, or Albert, or something or other, one of my uncles, that he claimed that he could do something, and you saw that it was just too unfrequently. The time that I said I could beat Michael Jordan in a game of one-on-one, Lauren almost came out of her seat and attacked find me for such heresy. Can this conclusion, then the next question is, how confident are we in this estimate? Can it be generalized? Can a cause and effect be legitimately drawn between here? So we try to do the statistics. We may try to do a simulation. We actually may use the math behind it. And does the strength of evidence conclude that it's just too unlikely to occur just by chance? So there's this idea of statistically significant, which actually has come under fire in several years, but we'll still use it for now and then kind of explain it a little bit later. So statistically significant which is the unplausible explanation for the differences versus something that, well, it could be plausible or could be believable. If I say I'm a 70% free throw shooter and I shoot 100 free throws and make 68, is that plausible enough if you're a 70% free throw shooter to only hit 68 out of 100 shots? Because you're just going to have variation. You know, what if I hit 42 shots out of 100? I think I'm probably getting to the point where I'm lying or something's not going there. It's just too implausible. Is it possible that a 70% free throw shooter can only make 42 out of 100? Possible, but so unlikely and so improbable that we'd have to take the original claim that I'm a 70% free throw shooter to bear. I think any professional basketball player should be able to shoot 70%, by the way. I know my shots. I have 69. If I were to make 2 more free throws, I could get 70%.
I was disagreeing with you.
Oh, you're disagreeing with me? Okay. Yeah, but I think women shoot free throws better than men too, so. What was that?
I think we do.
Well, I have some reasons for that as well, but that's another math seminar topic, so. If you want to ask me about why I think females shoot better, then I can tell you later.
Why do females shoot better?
Later! Later. The big thing is you have to pay attention to the key assumptions or else you may leap too quickly to an incorrect conclusion. All right, let's try this one. I did have it set up on my Plickers account. Who is more confident, the guy on the left or the guy on the right? Guy on the left or the guy on the right? Who's the more confident looking, the guy on the left or the guy on the right? How many vote for the guy on the left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many vote for the guy on the right? 1, 2, 3, 4, 5, 6, 7. Well, I just looked up some place for a House of Representatives. And this is what Utah's race in 2006. And so this guy won the election. And so what they did was, in the study, they gave people 2 faces and said which one looked more confident, not knowing who won or not. And then they kind of try to compare with the people that did win. Okay, do you understand that process? So they show them 2 pictures of politicians. They kind of say which is more confident, go there. So who has the more confident looking face then? So in this case then, they picked out 23 out of 32 or 72% of the correct winners. Could be a comment on our political system, maybe not. The question is, could this have happened just by chance alone? If it were a chance alone, what should have been the prediction or percentage? 50, about 50%. Now, just remember, a sample size dictates how precise our parameter is. We only took 32, so it's going to be a pretty wide margin. And the other part, if we increase the sample size from 32 to make it 128, 4 times as large, or 256, the sample error gets smaller. So we'll have a little bit more accuracy with our results. So our test here is a one sample test for proportions. The null hypothesis that P is 0.5. There is no difference in selecting competency by appearance. The alternative, oh no. It's not that. I don't know if there's a way that I can. Greater than 0.5. And people tend to make judgments about a candidate based on facial appearance. Assumptions, it's random, I guess. Normality, 32 times 23 over 32 is 23. 32 times 9 over 32 is 9. Uh-oh.
I have a question about the experiment.
Yeah.
The way they set up the survey. Is it they asked one person across 32 different races, or they asked 32 different people about one race?
I think they asked 32 people about one particular race.
But then, like, what if that guy actually does look confident, so then there's the probability that people chose him just because based off of that one race?
Yeah. So I think they'd have to repeat it over and over again. Make sure. Let me just kind of double check what I wrote.
Just repeat it with many people over several races, over many races. I don't know.
I think it was, come to think of it, it may have been a vote. So they had, so many people and they voted this way. This, I have to go back and look at the study a bit, but that's really a good point there.
Why did we say the null is P is greater than 0.5? Can it also be like way less than 0.5?
Yeah. But I think the alternative there was, can they predict more? That's kind of what we were looking at to see if it looked more. All right, let's take a look at how you could use Minitab for this case. We cannot use the z-test. Why? The normality is not done. But what we can do is use something else. Let's kind of take a look at what Minitab could provide. So I go to, well, is this a proportion or a mean?
Proportion.
It is a proportion, so I'm going to go to Basic Statistics, one proportion, and I'm going to summarize data and enter it in. Out of 32, they picked up 23. And let's go ahead and do a hypothesis test. The hypothesis proportion is 0.5. And I want to say that my proportion is bigger than that. And let's do it at 90% confidence. And here's where I have a choice between exact and normal approximation. I can't use the normal approximation here. I have to use the exact. And actually, come to think of it, if I use the normal approximation, I wonder if Minitab will give me a warning. Nope, it didn't. It should have, but it didn't. But that's my own fault for putting it in there. What I should do instead is use the exact method, and it will tell me that I use the exact method is used for this analysis. There I get to 71.9%. My lower bound was 0.59, and my p-value is 0.01. So if I draw this, just in this figure here, 0.5 would be my hypothesized mean. Here I have 0.719. And if I look to see what's bigger than 0.719, I get a p-value of 0.01. So I would reject the null hypothesis and claim that people do have tendency for more competency. Before I answer your question, let me just show you one other thing. If you look at this lower bound, what I'm saying is that my true proportion is bigger than 0.5925. does that contain my hypothesized mean? Does it contain 0.5 in there? No. And that's one way to check, is to see if your null hypothesis is within your confidence interval or not. If it's within your confidence interval, you don't have enough evidence to reject. If it's not in your confidence interval, then you can reject. Alex?
So the confidence interval is the confidence interval around the sample proportion.
Yeah, it's this estimate based on that sample proportion.
Right, okay. And so if the mean for your null hypothesis is not within that confidence interval, then it's not reasonable with whatever that confidence is to say that you can.
Right.
So if you increased.
Yeah, so if I increase this to 0.6, I could not reject the null hypothesis. Because 0.6 would be in that interval.
Sure, okay, so like if you increase your confidence interval.
Oh, to like
99.
from 0.90 to 0.95?
No. If you have a 99% confidence interval, wouldn't the lower bound be lower?
It would be, yes.
And so could that possibly encompass 0.5?
It could, but we can check.
And so if it did, then you could not reject the null hypothesis.
Yeah, and that's kind of where you have to just state what your you have to state what your confidence level is up front, so you don't like cheat.
Right.
So in this case, yes, you barely get in the 0.5. So at the 0.01 level, you would get it. You could not reject the null hypothesis because it's so wide. Yes, Abby?
What's the p-value again?
Great question. Great question. Hold on for 4 minutes, okay? So what we conclude is, at the 0.05 level, we conclude that voters do make judgments about confidence based on appearance. So we did that because we rejected the null hypothesis. Here I did one for double-sided, but...
So is your interval from your sample p to the lower than probability? And so if your null hypothesis is in there, then you can't reject it?
You don't reject it, right. Correct. In this case, I did a two-sided one. So the idea is your null hypothesis will generally be theta is equal to theta naught. And either you're going to have theta bigger than theta naught, in which case the implicit hypothesis is less than or equal to that. Theta is less than, my true parameter is less than what I'm claiming it to be, in which case really my null hypothesis is saying it's greater than or equal to, or they're not equal to each other. So that's a two-sided interval. So that's generally the setup in the big five and all the rest of them that come later. So you make a claim about a population parameter, and by the way, it can never be proven, only discredited as probably false. This is not mathematics class anymore. This is probably or plausibly kind of decisions are being made. And so this was the shark. You state the test, determine the null and alternative hypothesis, collect the necessary data, make sure the assumptions are met, and summarize the data into appropriate standardized test. Assuming the null hypothesis is true, find the p-value, and then write your conclusions. And then you look back and ahead to kind of see whether things work or not. So the definition, Abby, of a p-value is a little complicated and a little not so easily done. Okay. First of all, it is a probability. It's calculating the probability assuming the null hypothesis is true. And determine the p-value. Let's first decide which values of the test statistics are at least contradictory to the null hypothesis and the value from the sample. Basically saying, do you want a one-sided or two-sided? The smaller the p-value, the stronger the evidence against the null hypothesis. The larger the p-value, the less evidence there is against the null hypothesis. It is not the probability that the null hypothesis is true or false. That's a big one. It is not, just like we had with the confidence interval saying it's the probability that the parameter is contained in our confidence interval. No, the confidence interval is the method. What's the probability our method produces our parameter in there. A specific one does not tell us whether it is or not there. So the way that you can do this, if you take out your course pack and look in the very back of the book, to page 99. On page 99, and this is page 99, right there. The p-value of a data set is equal to the probability, presuming the null hypothesis to be true, of obtaining a result. Test statistic as favorable or more favorable to the alternative hypothesis than obtained by the data. This is something you'll need to memorize, by the way. So on page 99, under the p-value of a test, you can delete the first sentence, but the second sentence, the p-value of a data set equals the probability, presuming the null hypothesis is true, of obtaining a result as this. So in practice, we never accept the null hypothesis. We either reject or fail to reject. It's kind of like the courtroom of law. You're either guilty or not guilty. You're not innocent. They just didn't prove enough of your case to be guilty. Okay, you're either not guilty or guilty. You're not innocent. You're just either guilty or not guilty. Always check for randomness and always specify normality conditions for each of the big five. And for our big five, we're either going to look at a z-score or a t-score for the sample statistic and the null hypothesis. And your t-statistic and your z-statistic will vary depending on whether or not what your null hypothesis is. But in general, like we had our estimate plus or minus our multiplier times our standard error, the z statistic is sample statistic minus our parameter value divided by the standard error. It's the same sort of deal again and again and again. And if you have an alternative hypothesis two-sided, you're going to calculate the area on both sides. If your alternative hypothesis is less than or greater than, you're going to calculate the p-value on one side. So here's the definition again. Let's say this all together to close out class. I'll say the first fewer words, and then you repeat after me, except we're not supposed to do that with our mask on. So you have to whisper it into your mask so you don't blow out air. So the p-value of a data set equals the probability, presuming the null hypothesis to be true, of obtaining a test statistic that's favorable or more favorable to the alternative hypothesis than the value obtained by the data. Okay, you got about 3 weeks to memorize that particular thing. All right, we'll meet tomorrow in the computer lab and show how Minitab can speed up a lot of our work.